Hello, I'm Norman Wildberger. In today's lecture, we're going to carry on with this idea of connecting planar geometry, in particular the study of circles in the plane, with a three-dimensional relativistic geometry. Basically, geometry coming from Einstein's special theory of relativity as described by Minkowski. This shows that special relativity is actually really quite close to our everyday experience and can be understood purely in terms of elementary high school geometry, going back essentially to Euclid. So here's our two-dimensional plane, x and y coordinates as usual, and we're considering circles, actually signed circles. It's an important but subtle difference from the usual kind of circle. So what is a signed circle? Well, here's an example. It's an expression that involves a center, just a pair of numbers, there's a center, and down here a radius. All right. So here's one circle, and here's another circle. This one has center -2, 3 right here, and has radius 3/2. Okay, so those are signed circles. And what is the significance of the signed aspect? It's that we are allowing not just positive radii, but also negative radii as well. And so if one of these circles has a negative radius, we interpret that as meaning that instead of having the positive orientation in this direction, we're thinking about the circle as having a negative orientation in this way. So the sign of the radius is determining our orientation on the circle, with counterclockwise being the positive direction and clockwise being the negative direction. Okay, so then our idea is that we're going to connect one of these circles with a point, a single point in this three-dimensional space. Because there's three parameters that determine the circle, so we're going to associate to such a circle a point whose coordinates are the center coordinates, x and y, 2 and 1, and then the radius coordinate for the z component. So here's x, y, z space, our three-dimensional space as usual, and we're representing this circle in the plane by this particular point in this three-dimensional space. So it's 2 in the x direction, 1 in the y direction, and 1 in the z direction. And I remind you that you can picture that with a little box so that there's the point right there. This circle here, whose center is -2, 3, and whose radius is 3/2, is represented by the point or the vector -2, 3, 3/2. So that's -2 in the x direction, 3 in the y direction, and 3/2 in the z direction. It'll be up there somewhere. All right, so that's the basic idea that to a general signed circle, CABR, we're going to associate a vector ABR. And you can see that this is somehow easier because the vector is a simpler object than this expression for the circle. It encodes the same information. But now we have a point. We can think of this as a point in three-dimensional space. All right. In this three-dimensional space, there's a special plane, which is the actual plane of the xy plane. So that's the horizontal plane here. And that corresponds to points whose z-coordinate is 0. In other words, which have 0 radius. Those are essentially point circles, like this one down here. So here's a circle centered at 2, -3, with radius 0. It's just a point. That's represented on our diagram by the point 2, -3, 0, which is lying in this horizontal point plane in the three-dimensional space. So one very significant advantage of doing this is that when we're interested in the homothetic center of two circles, let me remind you what that is. So that's what we get when we take, say, these two circles here, and we're looking for a point where the two circles are in perspective, essentially, from that point, that one is obtained from the other by a dilation. So we could get that by drawing lines, drawing tangent lines, and then there would be a common point, maybe down here somewhere, all right? And from this point down here, a dilation would take this circle to this circle. And if we dilate not by this factor but by other factors, then we get a whole family of circles which are all dilates of this one. So as we go out, they become bigger. As we get in here, it will become sort of smaller and smaller as we approach this point. And on the other side, they would get bigger again with the opposite orientation. So you can kind of imagine a whole line of circles, all obtained from this one by dilating at this homothetic center. So this family of circles that we were drawing here corresponds in our three-dimensional situation with a line that joins our two circles. So all the points on this line correspond to circles in this family. So the homothetic center of two circles has a easy geometrical interpretation over in the relativistic space. It's the point where the line that joins the two circles meets the point plane. All right, so now let's exploit the fact that we know a lot about how to describe lines to get a formula for such a homothetic center. So let's suppose that we have two circles, C1 and C2. And in the plane, here are C1 and C2. Let's say C1 is now represented by the vector A1, B1, R1, and C2 is represented by the vector A2, B2, R2. Just another way of writing down what the sign circle is. And these are actually corresponding to points over here in the three-dimensional relativistic space. That might be the point C1 and the point C2 corresponding to these sign circles. And now let's have a look at this line, the line that joins C1 and C2. Well, we know that if we have two vectors, then the line that joins those vectors has a parametric kind of equation using convex linear combinations. By going back to one of our earlier lectures in the series, maybe around 3 or 4. So this affine combination or convex linear combination, 1 minus lambda C1 plus lambda C2. So we take this vector and multiply it by 1 minus lambda and take this vector and multiply it by lambda. Then that will give us a vector which is somewhere on this line. And as lambda varies, we're varying on that line. So it's a nice way of describing a line in the vector language. All right, so we might be interested in where this line meets our horizontal point plane, the plane where z equals 0. So if we look at the z-coordinate here, the z-coordinate will be 1 minus lambda times r1 plus lambda times r2. We might be interested in finding when that's equal to 0. Well, that's a linear equation in lambda, which we can solve. So just write it out. Solve for lambda, and you get lambda equals r1 over r1 minus r2. So that's the particular number that you have to put in here so that you're getting a point which lies on the line and also in the plane z equals 0. All right, so if lambda equals this number here, then you have to put that there. And then 1 minus lambda this will be 1 minus this. Okay, if you get a common denominator, that's minus r2 over r1 minus r2. So the vector that we get is minus r2 over r1 minus r2 times c1 plus r1 over r1 minus r2 times c2. Right, so that's a formula for the homothetic center of two circles, of the circle A1, B1, R1 and A2, B2, R2. So for example, in the example on the previous slide, we had C1 was minus 2, 3, 3 halves, and C2 equals 2, 1, 1. In this case, the R1 over R1 minus R2 will be, there's the R1, and there's the R2. So it's 3 halves over 3 halves minus 1. Just 3 halves over 1 half, which is 3. Right? So lambda is equal to 3, and then 1 minus lambda will be minus 2. So the formula is C0 equals minus 2C1 plus 3C2. And if you take minus 2 times this and add 3 times this, you get the point 10 minus 3, 0, which is pretty close to the point that I drew on the previous slide, representing that homothetic center of the two circles that we had there. So there's very explicit formulas that are utilizing the linear algebra, okay? So that now if you have two sine circles and you know their centers and radii, well, you have a nice formula, immediate formula for the homothetic center of those two sine circles. And I remind you that for sine circles, the homothetic center is unique. There's only one of them. Right. If you have two unsigned circles, well, there are two possible homothetic centers. But with sine circles, there's always only one. It's a very important aspect of the theory of sine circles. So I have quite a few things that I want you to do in today's lecture. Today's lecture is packed full of information and interesting developments. So please go slowly, take your time, spread it out over some days or weeks if you like. All right. So some good things to think about. Our first exercise is to practice finding some homothetic centers of circles. And let's start off with 3 circles. Okay, so here are 3 particular circles. So this is the circle whose center is at the point 1, 3, whose signed radius is 1. Here's a circle center 0, minus 1, whose signed radius is minus 2, so it corresponds to orientation in the other direction. And here's center 2, 1, and radius 3. All right, so now we have 3 sine circles. Any 2 of them determine a homothetic center. So you can pair up those 3 circles in 3 different ways. So there will be 3 homothetic centers. So you can practice finding homothetic centers. Find all 3 homothetic centers of pairs of these circles. And graph the whole situation. Just put everything on a planar graph to check that you've got things in the right positions and things are looking good. And then formulate a conjecture. So once you have that picture in front of you, I think a conjecture might leap out at you. And once you've formulated that conjecture, well, have a go at proving it. It's actually a theorem that goes back to the important French geometer Gaspard Monge. And our third exercise is to rewrite the formula for the homothetic center on the previous page, which had a star beside it, in this sort of alternate form, which shows that if here is the homothetic center in the 3-dimensional space of the circles represented by the points C1 and C2, then R1 times C2 minus C0, so this is the vector from here to here, equals R2 times the vector C1 minus C0, the vector from here to here. So this to this is this over this. It's going to be the same as R1 over R2. It's another way of thinking about where the homothetic center is, which makes a lot of sense. Okay, so I think it's a good idea if you pause the video here and have a go at these problems. In particular, try to get a grip on what this conjecture is and how you might prove it. All right, so pause the video, have a go at those, because I'm going to come back now and say more about this theorem. So pause the video, have a go at these problems, and then we'll come back and we can discuss this theorem. All right, so here is a theorem that you will have discovered if you have done that previous exercise correctly. It's that the 3 homothetic centers of 3 sine circles are collinear. And here's a proof that essentially just relies on our interpretation of sine circles as points in this 3-dimensional space. So the 3 points C1, C2, C3, which I've represented here by these points C1, C2, C3 in our 3-dimensional space, those 3 points determine a plane P. All right? 3 points in general determine a plane. There it is right there. And this plane meets the point plane z equals 0, that's our green horizontal plane, in a line L. All right, so there's some line of intersection of the plane P with the point plane z equals 0. All right, so now let's think about the homothetic centers. How do we find the homothetic center of C1 and C2? Well, we join those 2 points with a line, and we see where the line meets the horizontal plane, the point plane. And similarly, to find the homothetic centers of the circles C1 and C3, we draw that line through there and see where that line again meets the point plane z equals 0. And similarly for C2 and C3, another line which will meet this point plane in another point. And now it's obvious that the places where these 3 lines meet the point plane are all going to be on this line L, because each one of these lines individually lies in P, and P meets the plane in this line L. So the places where any one of these individual lines meet the point plane has to lie on L. So the 3 homothetic centers lie on this line. So those are actually points in the plane, and the collinearity of these points is corresponding to the collinearity of those points in the original xy plane that we started with. All right, so it's an interesting now additional comment to make, that if we have 3 unsigned circles, right, so let's say you have one circle here, another circle here, another circle here. All right, so then we can orient these circles in lots of different ways. So we could maybe orient this one this way, orient this one this way, and orient this one in that direction there. Given such an orientation, we can find homothetic centers. So we draw a homothetic center. There's one right there. And this one here will be, we have to draw tangent lines that are like this. There's another homothetic center. And maybe hard to see, there's another tangent pair meeting right there. And so those 3 are 3 homothetic centers lying on a Monge line. All right, but that was only one of actually 8 possible ways of orienting those 3 circles. Now if we had oriented each one of them in the opposite way, well, then the homothetic centers would be unchanged. There's really only 4 essentially different ways of orienting the circles with respect to each other. So we end up getting 4 such Monge lines of homothetic centers. That's one of them, but there will be 3 more. It's a very nice configuration that naturally goes with 3 circles in the plane. Now the relativistic aspect of this story really takes shape once we introduce a notion of measurement between 2 points in our 3-dimensional space. And as you probably know by now, we try not to use distance in terms of measuring points. We'd much rather use a notion of quadrants, which is much more natural from a linear algebraic point of view. And in fact, it's essential when you go to relativistic geometry that you drop this idea of distance and go to the more general and pleasant algebraic notion of quadrants, exactly as Einstein suggested. All right, so if we have 2 points in 3-dimensional space representing signed circles, say A1, B1, R1, and A2, B2, R2, so we can think of these as being 2 signed circles, then the quadrants between them is defined in this way. A2 minus A1 squared plus B2 minus B1 squared minus R2 minus R1 squared. This is our definition of the quadrants between these 2 signed circles. And I showed you last time that there was a geometrical interpretation of this quadrants. It's a very natural way of thinking about how far apart are 2 circles in the plane. Okay, so if here is the circle, say C1, and here's the circle C2, and for illustrative purposes, I've got them oriented in the same direction, but it's not necessary that they be oriented similarly. It also works if they're oriented in opposite ways. But if they're oriented this way, then their homothetic center will be out here. And in this case, this homothetic center is also the place where the two tangents, the common tangents of the circle, meet. And the interpretation of this number is that it's exactly the Euclidean quadrants between those points of tangency between the two circles. So if we look at these 2 points and ask, what's the Euclidean quadrants between them? The answer is this. And I remind you, by Euclidean quadrants, sometimes we might call that the blue quadrants in the plane. That's just the regular quadrants where you take the sum of the difference in x coordinates squared and the difference of y coordinates squared. So it's the square of the usual distance if you're believing in square roots and distances. Which we don't have to in this story, right? Because it's completely algebraic. This is linear algebra. So if we look at this diagram here, I'd just like to point out that the dilation, which has centered O and sends this circle to this circle, so we're dilating everything by a certain factor centered here, taking this circle to here, will also send this particular point to this point, and this point to this point, and in fact this point to this one, and this one to this one. So there's sort of rational ways of constructing this homothetic center by just connecting this point and this point with a line, connecting this point and this point with a line, connecting this point and this point with a line, or this one and this one with a line, and those lines will all meet at this point here. All right, so this is one possible interpretation of the quadrants between sine circles in the situation where we have the circle sort of being separated, where there is a common visible tangent to them. In this relativistic geometry, with the quadrants that we've defined, a very important kind of situation is when two circles have quadrants of 0 between them. That has an important geometrical significance. It corresponds to tangency of the two sine circles. So if the quadrants between this circle and this circle equal 0, well, that's just saying that the difference between the a's squared plus the difference between the b's squared equals the difference between the r's squared. And here are some examples of such tangency. So here's a circle C1, this one right here. And I've shown you a few circles which are tangent to it, in the sense that the quadrants between these circles is 0. So here's a circle C2. All right? And notice that it's tangent in the obvious way. But it's also tangent in the sense that as we move on both circles in the directions of the orientations, we're moving in the same direction at the point of tangency. That's an important aspect of this tangency for sine circles. Similarly, this circle C3 going this way is also tangent to this circle C1. Here the point of tangency is there, and they're both going in the same direction. Another example of a kind of tangency is this bigger circle C4, oriented this way, which is also tangent to C1 at this point here, where they meet. Now over in our three-dimensional situation, such a condition here really determines a cone. So if we think of C1 as being fixed, and we think of C2 as being sort of variable, then the set of vectors that satisfy this will be a cone that looks like this. All right. And this cone is consisting of those points that correspond to circles which are tangent to C1. So in this particular example, for example, C2 over here, this circle here, it's got, there's C1 and C2 is down here, I guess. So it has a negative radius because it's going the opposite direction there, so it's actually below the equatorial z equals 0 point plane. There it is down there. But it's still on this cone. All right, the cone represents all the sine circles which are tangent to this one. This circle C3 over here would correspond to, it's also a positive radius, so it would be above our point plane. It would still be on the surface of this cone, maybe right about there. That's supposed to represent a point that's actually still on the cone. C4 over here has a bigger radius, so it'll be higher up, but it will still be on this cone, on the top part of the cone. So you can think about this cone actually consists of lines. Right? The cone is actually obtained by lines sweeping out like this. And if we take any one of those lines, say this line here, that line corresponds to a whole family of circles which are all tangent to the original one. For example, this line here that passes through C2 would include not just this circle, but also sort of bigger circles that are still tangent at the same point. So all these circles I'm drawing here like this, and even the ones that go like this, are all going to be tangent to C1 at this point here. So it's sort of a one-parameter family of circles tangent to C1 represented by that line there. So in physics, such a cone is called a light cone. Okay, it represents sort of the motions of photons in space-time. Here we're seeing a very concrete physical geometrical interpretation of that light cone in terms of sine circles which are tangent to a given sine circle, namely to the circle that corresponds to the vertex of the cone. And now let's extend the discussion a little bit by considering two fixed circles. So suppose we have a circle C1 and another circle C2 in the plane, and they're fixed. And we're interested in the question of finding other circles which are mutually tangent to both C1 and C2. For example, perhaps this circle here. So here's a circle which is tangent to both C1 and C2. Notice that it's going in the same direction as each of C1 and C2 where they meet. But this is not the only one. There's a whole bunch of these. So here's another one. And inside here there would be a sort of smaller one, actually going this direction. You can imagine a whole bunch of circles getting bigger as we go in that direction, or bigger over here. A little bit of thought shows that that's sort of only one of two families of such circles. There's also another family of circles which are tangent to C1 and C2 sort of around the outside. So a circle that goes like this, for example, and it has its center somewhere here. If we move the center over here, well then we could get a bigger circle that's tangent to both of them. So it looks rather complicated when we think about things in the planar situation. But when we go to the three-dimensional situation, we learn something because of, well, we have more dimensions and things are a little bit more linear over here. So we're going up in dimensions, that makes it more complicated, but things are more linear, and that's a big advantage. So what does it mean to be tangent to C1? Well, it means that the quadrants between whatever circle we're thinking about and C1 is 0. There's the equation representing quadrants of 0 between the circle XYZ and the circle A1, B1, C1. And here's the equation representing tangency with C2. Now over in the three-dimensional space, this first equation determines, as we've seen, a cone. Geometrically, that's just a cone in the three-dimensional space whose vertex is at C1. And here this represents a cone whose vertex is C2. So over here in our three-dimensional situation, this problem is really a question of describing the intersection of these two cones. We're looking for points in the three-dimensional space which lie on both this cone and this cone. That means that they're going to be tangent to both C1 and C2. All right, so now here's an interesting exercise for you. Show that these two cones meet in a plane. So there's actually a plane shown in green here, so that all the points that are in the intersection of those two cones are really also on this plane. So it's a question of looking at these two equations and doing some kind of linear algebra manipulations to try to extract from those two equations the equation of a plane. I remind you, a plane is a linear equation in x, y, and z. And once you've done that, well, you can immediately conclude that what we're getting is really a conic section. Because we know that once we have a plane meeting a cone, well, that's going to be a conic section. And I've shown that here in these two branches, sort of two parts of a hyperbola. So the geometry of the intersection of the cone is really just a hyperbola in this three-dimensional space. And the points on this hyperbola correspond to the two families of circles which are mutually tangent to both C1 and C2. So sort of the projection of the hyperbolas onto the xy plane are giving us the centers, and that's that hyperbola there that we're seeing in the dotted lines in the diagram. So a great little exercise for you to think about, and showing the power, I think, of the three-dimensional story in understanding this somewhat complicated story in two dimensions. Okay, we must now talk about this famous problem of Apollonius, going back more than 2,000 years, and described at some greater length in the famous math problem series number 3. So the problem of Apollonius is a construction problem, and the most general problem is this one here, where you have three circles, C1, C2, and C3, and Apollonius asks, how do we construct circles which are tangent to all three circles? A very famous problem that's seen a lot of interest. Many important mathematicians have worked on this problem and aspects of it. All right, so we're going to ask the story in the context of sine circles. So if we have three sine circles, there's C1, C2, and C3 in green. So how do we construct sine circles which are tangent to all three? Well, with this configuration of circles, there are two solutions. There's one right inside here, and there's another one that's outside, touching all the three circles outside. And so with three sine circles, there are typically two solutions. And if you then remove the orientation, so with three unsigned circles, there are 4 times that. Essentially because there are sort of 4 different ways of putting orientations on the circles with respect to each other. 8 altogether, but 4 after you sort of divide by symmetry. And this suggests that in general there are going to be 8 solutions to the Apollonius problem. All right, so for those of you with an interest in geometry and like to do a little bit of sort of additional exploration on your own, here's a fabulous exercise that you can now use this relativistic framework that we've set up, with these coordinates and equations of cones and so on, and especially the previous problem, to solve this problem and interpret it in relativistic geometry. All right, so you can now actually write down, given 3 vectors representing sine circles, you can write down the relevant equations of the various planes involved and whether there are solutions or not. And it turns out that there's a very nice interpretation of what's going on there using a bit of relativistic triangle geometry that you might like to explore. So that's a great exercise. I'll probably at some point in the famous math problem series I will give a solution to this in this direction. It's certainly a very famous problem, and it's nice that it's really involving relativistic geometry. When we have a situation where we have 2 different ways of thinking about something connected in a very nice way, there's usually opportunities for conveying information in both directions. So we've been talking about how the relativistic setup helps us think about planar problems involving circles. But conversely, the setup also allows us to interpret relativistic geometrical questions in a planar form. So it allows us to get our hands on relativistic geometry in a way that's very concrete and down to earth. Let me illustrate what I'm talking about here by going back to this very important diagram of spheres in our relativistic three-dimensional geometry, our red geometry in 3 dimensions. So I remind you that here's sort of the basic quadratic form, x squared plus y squared minus z squared. And we're thinking about spheres in this 3-dimensional space. So basically where you set this thing equal to 0 or equal to 1 or equal to minus 1 or equal to 5 or whatever. So if you set this equal to 0, you get this sphere called S0, which is just the cone whose apex is the origin. If you set this equal to plus 1, you get the sphere we might call S1, which is a hyperboloid of revolution, what you get when you take this hyperbola here and you revolve it around the z-axis. It's a hyperboloid of 1 sheet. And S sub minus 1, what you get when you set this equal to minus 1, is a hyperboloid of 2 sheets. What you get when you take this hyperbola and again revolve it around the z-axis. So it has a hyperbolic cup in this direction, hyperbolic cup in that direction. So a natural question is, how do we interpret what these spheres are? Can we visualize these spheres in a reasonable way? And we can do that. We can do that now by connecting what's going on in this 3-dimensional space with our story of sine circles in the plane. And it's very interesting when we do this. So let me start, I suppose, with the S0, okay, which we've already sort of talked about. So how do we think about points which lie on this cone S0? Well, these are just corresponding to circles which are tangent to this circle here. Now this circle here is just this single point circle in the xy plane. So we're talking about circles here, and when I say circles I mean sine circles, which are tangent to this one. So for example, if we took some particular direction that we're going in, that would correspond to some direction here. We're thinking about all the circles whose centers are in that direction, which are tangent to this circle, namely which go through it. Right? So there would be one there, and maybe in this direction, and then there'd be a bigger one there, for example. Okay. You make bigger and bigger circles going that direction, that would sort of correspond to going out in this direction here. Or we could go in this direction here, and essentially go in the opposite direction. That would still lie on the same line. All right, so the cone itself, the light cone itself, has an interpretation here as just all the circles, sine circles in the plane, which in fact pass through the origin. That's all. And it's sort of pretty natural that those circles are arranged in lines. Right? Given any line, you can look at all the circles whose center is on that line, which pass through the origin. That's a line of circles. All right, now let's have a look at, say, this hyperboloid of 2 sheets. Let's have a look at just this upper sheet here, and say that point there. What does that correspond to? Well, that corresponds to a circle whose center is at the origin and whose radius is 1. I'm calling that C2. Here it is right here. All right, here's a circle, positive radius of 1, center at the origin. All right, so what do the other circles that lie on this hyperbola, what property do they have? Well, their property is that they're all of quadrants 1 from this point here. And what does that mean over here? Well, it means that the quadrants of such a circle, and here's such a circle, with this point circle is 1. And that means that this quantity here, which is the perpendicular quadrants, perpendicular from the line joining the centers, that quadrant is equal to 1. So what we get is a family of circles. If we're just going in this direction, we're getting all the circles that in fact pass through those 2 points. That's called a pencil of circles. So it gives us a pencil of circles, sort of like a 1-parameter family of circles, and includes this one here, and includes C3, which was this point here, and C4, which is down here, also passing through these 2 points. So as we move along here in the hyperboloid, we are moving through all the circles which are positively oriented, which passing through these 2 points. If we looked at the corresponding sort of section of the hyperboloid down here, then we'd be looking at really the same circles, but they'd all have negative orientations. And if we went in some different direction, well, instead of having all the centers along here, we'd be looking at a pencil of circles whose centers would all be on some other line like that, still going through here. So this hyperboloid of 2 sheets has a very concrete realization. You can think about the points on this hyperboloid as corresponding exactly to circles which are in the plane and which in fact meet this given circle, what we're calling C2, in a pair of opposite diametrically opposed points. Okay, let's have a look at the hyperboloid of 1 sheet passing through C1. It's a little bit different. So C1, this point here, is in the point plane. So it's in the XY plane. It corresponds over here to a point. What point is that? Well, it's a point, which is the point 0, 1. So 0 in the X direction, 1 in the Y direction. That's exactly this point here in the plane. Right? So this point circle there corresponds to this point in the 3-dimensional space. What happens when we look at other points on this hyperboloid? Let's say we move along here on this branch. What's happening? Well, the critical thing is that we're always having quadrants of 0 with this point here. So that means we're looking at all circles whose quadrants from here is exactly 1. What does that mean? It means that I'm going to draw such a circle for you. So here's a quadrant, Euclidean quadrants of 1. So if I take a circle which is perpendicular here, like that, maybe it has its center over here somewhere. So a circle like this, which has its center on the y-axis and is perpendicular to this basic unit circle, then it will mean that the quadrants from here to this circle is this perpendicular quadrants, like a power. And that's 1 because this is a circle of quadrants 1 in the plane. So such a circle is corresponding to a point on this hyperbola. And as we move this sort of line further down like this, then we get bigger and bigger circles that are perpendicular to the given circle. So there's a sort of a branch this way, and then there's a corresponding branch down here. Let's see if I can draw that. Here's our circle. And so the center here would be somewhere over here. And that would have that would correspond to something over here, depending on the radius. All right, so basically what happens is this hyperboloid of 1 sheet corresponds to all the circles in the plane which are perpendicular to this given unit circle. A very nice interpretation of this hyperboloid geometrically in terms of another very important pencil of circles. So if one studies circle geometry, these pencils of circles, exactly the two kinds of pencils that I'm talking about here, play a big role. And we see that they're naturally connected over here with the geometry of these hyperboloids in this relativistic setting. And conversely, if you're wanting to visualize what's going on with this relativistic setting and you want to understand these hyperboloids concretely and explicitly, one way of doing it is to think in terms about the geometry of sine circles in the plane. So we've done a lot of work today, a lot of different concepts, a lot of interesting diagrams, a lot of stuff to think about, so go slowly, right? Take it easy. Look at some examples, try to work things out yourself. A lot of potential for learning interesting stuff here. So I'd like to finish by answering a question that I left you with in our last video, which is really, how does one think about this relativistic quadrants in general? Not just for circles which are nicely situated so there's a common tangent. What happens if the circles are inside each other or overlapping? Or with different orientations? Is there some sort of uniform way of thinking about the relativistic quadrants between two sine circles? Well, it turns out there is, and I'd want to show you this theorem. And I'm going to show it to you in this case here because it's familiar, but in fact it's a very general fact. So here are two sine circles, C1 and C2, and we've seen that they have a unique homothetic center. All right, so in this case, there's a common tangent, and we were thinking about the quadrants of the circles as being the Euclidean quadrants between the common tangent points. But there's another way, a more flexible way of thinking about what this relativistic quadrant is. Okay. And what we do is we choose a line through the homothetic center which meets both of these circles. Now you can do that for sure because you can take, we have these four standard points, and if you connect corresponding standard points, then you automatically get the homothetic center. So you can certainly use those standard 4 points to do this. But in fact, it works for any line that meets the two circles. So imagine here is a line that meets the two circles. And suppose it meets them at the points A1, B1 and A2, B2. Okay, and an important condition is that our labeling is such that A1 and A2 correspond and B1 and B2 correspond. What that means is that if we're considering the dilation whose center is O, that sends this circle to this circle, then that dilation will send A2 to A1 and B2 to B1. All right, so then the theorem is that the quadrants between the two circles squared equals the product of the Euclidean quadrants between A1 and A2 and the Euclidean quadrants between B1 and B2. All right, so the Euclidean quadrants here, I'm denoting it by little b just to remind us. This is the Euclidean blue quadrants in this two-dimensional situation. This is the relativistic quadrants between the two circles, involving the minus sign. And this is independent of where these points are. So you move this around, then these points move, but this product of quadrants doesn't change. In particular, when they become a tangent like this, then both A1 and B1 become a single point, and A2 and B2 become a single point, and these things are the same. All right, in that case, we're just getting the quadrants is equal to that tangential quadrants. But this formula works even if one of the circles is inside each other, in which case the quadrants might have a minus sign. These are all Euclidean quadrants, so they're always positive. That's sort of taken care of by this square here. Another important point is that if C2, say the second circle, reduces to a point, then A2 and B2 coincide, and these two quantities become the two quadrants involved in Steiner's theorem that express the power of a point with respect to a circle as a product of two quadrants from the point to the 2 points on the circle. So this is a generalization of Steiner's theorem from a point in a circle to two circles. Okay, and so your final exercise is to try to verify this, get a sense for it, draw some circles using a dynamic geometry package like GeoGebra or CAR or GSP. See if it works. In our next video, we want to move a little bit towards physics. So we're going to talk a little bit about some high school physics from a linear algebra point of view. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.